had the same sense that I had when I first met him originally. I was starting to familiarize myself with his work, and that is I had a suspicion that I've never fully been able to get rid of, that he's actually a whole collective of people. He does the work of many men. And I'll give you an example of what I mean by this. He received his medical degree from the University of Bochum-Essen in Germany in 1989. He's originally from Germany. He received an MA in medicine from the University of München in 1990, an MA in philosophy from the University of Bochum, Germany, 1992. Then he went and got another doctoral degree, a PhD in psychiatry, from the University of Magdeburg in 1998. And then, apparently that wasn't enough, he got a PhD in philosophy from the University of Dusseldorf in 1999. He is at the University of Ottawa, where he is professor of neuroscience, psychiatry, and philosophy. And he takes a transdisciplinary approach to understanding the neural mechanisms underlying mental features like the self and consciousness, and philosophical issues like the mind-brain problem. And he supervises students and postdocs across these different disciplines. I was going to do the usual thing of giving you a count of his publications and so on, but I ran into this limit because I can't count that high. So instead, I'm just going to tell you that he has 124 first-authored papers. I gave up on counting the other ones. It's only a fraction of the overall number. There's a further 41 first-authored book chapters. Forget the numbers. I don't think that's what's interesting. I think what's interesting is the range of disciplines that he's published in. Neuroimaging journals, schizophrenia journals, cognitive science, biological psychiatry, ethics, philosophy of mind, philosophy of science. And I'll read you some book titles. He's the author of several books as well, both in English and in German. Here are some English titles will give you an idea of the breadth of his interests. Neurophilosophy and the Healthy Mind, Minding the Brain, A Guide to the Philosophy of Neuroscience, Unlocking the Brain, Philosophy of the Brain. So he really is at this meeting point of the sciences and the humanities, of theory and of clinical practice. And I think that's all you need to hear from me. So without further ado, Professor George Northup, thank you for joining us.
Yeah, thank you very much for the kind introduction and invitation. And you know, in the life of a psychiatrist, you get many diagnoses from your colleagues. But the diagnosis of multiple personality disorder, I never got. Yeah. So let me make the talk here. No, this is the speech here. Where can we make this? Oh, where is it here?
Here's what we'll do. I think if we hit here.
Ah, okay, it's there. Okay, because it's usual. Okay, got it. So I start with a question, because as you already heard, I'm sort of working in between theory and empirical domains. And one of the really important things is for the question I'm targeting, as you already heard, is really right between brain and mind. And the main question is really here, how do neuronal features, neuronal states, transform and translate into mental features, like sense of self, consciousness, psychiatric symptoms. This question may sound banal or trivial to you, but we don't really have an answer these days to this. So this is the central question of my talk, and I will make you a suggestion of that. Here you might have seen this picture from a very famous movie, Frankenstein, highly recommended to download. And the question is really here, as I already said, how is it possible, Arthur Schopenhauer, philosopher in the 19th century in Germany, considered the brain a gray, pulpy device. I added the gruesome. And it's really the question, how does that can yield mental features like self, consciousness, and psychiatric symptoms? And for that, before showing you some data, I will present you two different models of brain. Because as you may know, the physicists, mathematicians know very well, the kind of model you presuppose strongly determines the kind of experimental paradigms, designs, and analysis you will do. And my claim is that we currently do not have a proper model of brain. And I will demonstrate that. So, imagine a car. The brain, usually the traditional and also the most predominant view of the brain is that the brain is like a car. So what is it? So you push the gas pedal. It's not yet a self-driving car. Yeah. So you still push the gas pedal, and the degree to which you push the gas pedal is proportional, linearly related to the degree of speed you have. Yeah. The usual way. So, and that is basically, it's purely mechanical. And that's in a way is the predominant view of the brain these days. So you can see here, this is, you see this also in the animal literature, in the human literature, and ultimately we also do psychotherapy along those lines, that we present certain stimuli, here's the Colosseum of Rome, and then we see what activity change we can observe in the brain. On the right, you see what is called stimulus-induced activity. And what is most important, that we assume the degree of activity on the right, the stimulus-induced activity, to be directly proportional and sufficiently related to the stimulus we give. So this is a direct, very mechanical view of the brain. The degree to which you push the gas pedal is proportional to the speed. The degree of stimulus, the kind of stimulus you give, is directly proportional and sufficient for the neuronal activity. So now, of course, the question then raises, where do consciousness and sense of self come from? Because they have no place in that model. Yeah? The neuronal activity is directly sufficiently related to the stimulus, but where on earth, why do we perceive something at all? Why are you conscious? Unfortunately, I cannot see you much because it's so dark. Yeah? So I cannot know whether you're conscious or not. Maybe you can tell me. Yeah? Particularly when you are unconscious, you have to tell me. Yeah? So this is a real question. Yeah, and I was hurt. Thank you very much. Yeah, enlightenment. Yeah, so you really so this is the question, and then of course the people think there must be a special factor, an add-on factor. That is the, let's say, consciousness factor, like information integration theory, Tononi. As brilliant as the theory is, then something is added on. Or global neuronal workspace theories, Dehaene, some globalization of neuronal activity. So, and they still in that model. However, you can also imagine a different model. The brain is not like a car. So what do I show here? Now imagine you step out of the campus here and you see your motorbike, your bicycle, or your car suddenly moving back and forth. And you're not yet on the motorbike or cycle or within the car. Yeah, so it moves back and forth and it moves spontaneously. This is important, and it moves, as I try to indicate here, in certain spatio-temporal trajectories, a certain spatio-temporal pattern. And that continues to fluctuate. You said, am I crazy? I say, yes. Yeah, and that's exactly what your brain continuously does. It continuously oscillates, fluctuates, tries different spatio-temporal pattern. Imagine a tennis player, Roger Federer, Australian Open. He just reached the half final this morning, to my delight. So he's constantly, before waiting for the service, he's constantly doing this. Yeah, trying to mapping the spatio-temporal territory within which the potential stimulus / the service from the other guy could come. Yeah? And this is exactly what your brain does. And that leads to a different model of the brain. So here, you see, I didn't put in an animation here, but you see, first you start with the brain and you see this orange line there in the middle. This is a fluctuation. And that fluctuates. And depending on the timing of that fluctuation, the stimulus will have strong effects or not. And now the assumption of my model is that this spontaneous activity and its interaction with the stimulus is central for adding the mental component to our cognition. Meaning the mental component is sense of self and consciousness. I will show you several results about self. I will not show you results about consciousness. You can look that up on my website. And so the main idea is that this spontaneous activity and its spatiotemporal pattern is central for mental features, for sense of self, and I will show at the end, in the second part of my talk, for psychiatric symptoms. So ultimately, the claim is that mental features are spatiotemporal features of the brain's spontaneous activities and its spatiotemporal structure. And you will see what I mean by that. I hope I can provide you some flash. And this is really sort of, if you want to say so, a resting state or spontaneous activity model of the brain, or more precise, a spatiotemporal model of the brain. And this is very different from the cognitive model of brain, where you have specific contents and you assume that these contents have a specific representation in the brain. So, this is my talk about, and I want to show you the first part of my talk is about the sense of self. And then in the second part, I will make a transition to psychiatric disorder, particular focus on one disorder, bipolar disorder. And I will try to give you some life, put some meat to the bones, to the spatiotemporal bones of this spontaneous activity. So, what is a self? Since you're here in this room, I must assume that you somewhat got up this morning, and you might have also looked into the mirror. And then you saw, yeah, this is me. You probably weren't even aware of it. I assume that this was sort of pre-conscious, because usually you just take it for granted. It's tacit. Yeah? Sort of it's pre-conscious, conscious is on the border. And if you're doing psychotherapy, you know that much of what happens in psychotherapy is exactly at this level. It's unconscious, pre-conscious, and so on and so on. Yeah? So, and that's the same. And when you have this, you say, yeah, this is me, and you also have a feeling that it is me. A sense. I like to use the term sense. Philosophers use the term of experience, subjective experience, a sense of self. And this is not something to taken for granted, because as a psychiatrist, I know very well that the sense of self can change. I had patients, particularly with schizophrenia, who experience themselves as a different self. Yeah, I met, particularly when I was back working in Germany, I met a couple of Jesuses. Actually, one very interesting story here was that once on an inpatient ward, there were two schizophrenic patients who both claimed to be Jesus. And both also dressed like Jesus, with a beard and long white robe and so on. So, and of course, as a philosopher, it's all about logic. So I asked one of the patients, "You're Jesus?" "Yes, yes, I'm sure. But there's another Jesus on the ward. How is that possible?" So the schizophrenic patient said, "The other guy is wrong." Very logical answer. Then I asked the other guy, same thing. The other guy is wrong. Yeah? So when in China, I recently met somebody who claimed to be Chairman Mao. And it's quite interesting that we call this ego disorders, that they usually assume the identity of a famous person. Why that is so, I don't know. Yeah? So, what does this tell us? That your sense of self is not a given. Yeah? And when you argue with these patients, you are not Jesus, you are like this, they will say, no, I'm Jesus. And this is your feeling, because your sense and your feeling of self gives you the certainty. You know that. And this certainty, that gives you sort of your, makes part of yourself. So, then the question is, where on earth is the sense of self coming from? Obviously, it has something to do with the brain, because if you have changes in your brain, you can have changes in your sense of self. So how can you test this? You can test this in various ways. You can, for instance, pictures of your own self or your face, or you can show your own name, or you can present your own name compared with another name, or autobiographical events, and you can all do that while your brain is scanned in fMRI and EEG. So, and that's exactly, I show you a couple of data. So here that was early on. We analyzed all those studies who compared self versus non-self, own name, other name, in different domains. You can see this here, either spatial, verbal, autobiographical in the memory domain, face, own emotions, other emotions, and so on and so on. And what we found at the time, and it still holds today, that this is a view of one of the hemispheres of the brain, right the middle, and it is really that all these dots and spots are the different activations when you compare self versus non-self. And what you can really see is that it's really right in the middle of the brain. So that's why, so we said maybe these regions have a special significance, and we called them cortical midline structures, because it's the cortex of your brain and it's right in the middle. Yeah, the good golden middle room yourself seems to be in the brain, somewhat related to that. So here I show you a picture of the different cortical midline structures, as we coined them. Here you can see the medial prefrontal cortex, perigenital anterior cingulate cortex. Then in the back you see the PCC, posterior cingulate cortex, medial parietal cortex, MPC, and other regions. So each of these regions contributes a special thing, but often they're co-activated. There are also some other regions activated in the self. So these are not, and these regions also activate other functions, like for instance mind wandering. When you find this lecture completely boring and you just withdraw internally and you just follow your own thoughts and you don't care, that's when your cortical midline structures will be a lot activated. However, when you pay a lot of attention to me, your midline structures may be not as strongly involved, because then other regions are involved. So sort of the midline structures then recede in the background. Yeah. So when you remember the two models of the brain. When you apply the first model, remember, you present a stimulus and you see in stimulus-induced activity, and there's direct linear relationship between stimulus-induced activity and stimulus. It's like the gas pedal thing. Remember that. And you would expect that important stimuli induce stronger activity in the brain, so that they stand out more. Same, when you push more, you get more speed. And you would expect that your sense of self, yourself, is the most important stimulus for you. Yeah? So, because this basically makes you survive, this provides you personal identity, self-continuity, and blah, 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 blah. Without self, you're lost. As a psychiatrist, I can tell you a lot about that. Yeah? Sometimes I'm losing my own self, yeah? And so, what is important, and then you would expect that your self induces the strongest activity change in the brain. So you would expect that your self has the strongest activity change when compared to the ongoing spontaneous or resting state activity, as we brain imager call it. However, and that we tested. So what we here did, then we did a study where we compared self-related activity to the own name, autobiographical studies, and pure spontaneous activity levels. And the result, and it was very surprising, what we found that the degree of activity, particularly during the own self, does not diverge much from the ongoing spontaneous activity. So exactly the opposite. Self-related activity does not stand out when compared to the ongoing spontaneous activity. And this is what I show here. It's the overlap, the red zones, so the self-related activity. DMN means default mode networks. These are basically all the spontaneous activity levels. And the default mode network is a central network, again, closely overlapping with these cortical midline structures, and it shows a particular high levels of spontaneous activity. And interestingly, these two regions and another region, I will come back to that, the insula, strongly overlapped between spontaneous activity and self. So when you hear your own name, you will not have much activity changes in these regions. when compared to your ongoing spontaneous activity. It's a strange thing. This has been confirmed by others and other studies, because if it's really true, and I show you more support for that, it means that your self is already encoded or present in your spontaneous activity. Even if you don't do anything, your self is always with you. If you apply a common sense view, that makes perfect sense, because your self is always with you. I switched continents several times. I constantly travel to China. I can never leave myself behind. Yeah, always comes with me. However, when you take a scientific view, you can say that cannot be, because your self is subjective. Your spontaneous activity cannot be subjective. It must be purely objective. Yeah. So when I had these findings, that really made me change my view. The brain, from the view, the brain is like a car, the cognitive model of the brain, or the behavioristic model, is ultimately the same thing, to a sort of more spontaneous or spatio-temporal view of the brain, where central features are in this spatio-temporal structure. So, what do we do with these findings? So the question is now, so we had a strong overlap between the brain's spontaneous activity and the sense of self. And now, of course, the question is information about yourself encoded and contained already in your spontaneous activity? And if so, in what kind of features of the spontaneous activity is information about yourself encoded and contained? So, and that, of course, that's where I'm coming back. You remember the model, the car is not like a brain. Remember, I showed this spatio-temporal pattern. And that's exactly where I say the information about yourself is encoded in the spatio-temporal pattern of your spontaneous activity. And I show you a couple of findings. We have a lot of other findings in the pipeline, because it's really a major line of research. Yeah? So, I show you this one. So the question is basically, if there's an overlap, is your self is encoded in the self? It's like you're looking for a common currency between the brain and the self. So it's like we are speaking the same language. You speak English, or understand English, I hope so, and I speak English. So we can communicate, and I can transform some of my ideas into your thoughts in your mind or head. Same here. Maybe there's a certain spatio-temporal structure in your spontaneous activity, and that can be transformed into your sense of self and a certain spatio-temporal structure. One feature is, for instance, your self is always there. So it shows a certain temporal continuity, which is usually not interrupted. I have schizophrenic patients where that temporal continuity of the sense of self is interrupted / fragmented, temporal fragmentation. Ask the patients, you see it in the paintings, this fragmentation, you see it in the paintings in your psychotherapy rooms you showed me. It's very impressive. You see it in the painting. The person has no temporal continuity. It's very fragmented. That's the way he perceives. Yeah? And and this is what we tested here. So that means we need to look at the brain in terms of a spatial and temporal structure. What do I mean by structure? Give you an example here. The brain has neuronal activity, and it continuously fluctuates. It oscillates. And it oscillates in different frequencies, faster, slower. And this is what you can see here. This is the frequency range of the brain. You see in the very low there, infraslow. This is where you use fMRI. And if you go into higher frequency, from 1 Hertz to 40, 180, I didn't show this here, you do use EEG or MEG. And what is very important here, the slower the frequency, the more power. Yeah? So the faster frequencies are not as strong. They're much weaker in their power than the slower frequencies. So, and that relationship in the power between faster and slower frequencies, sort of a balance, provides you with a certain temporal structure. Yeah? And that temporal structure here, I indicate this with spontaneous activity. If somebody of you has an engineer background, she or he probably knows the power law, scale-free distribution, and this is what you call this relationship between the different powers of the different frequencies. You can measure that by what is called the power law or scale-free activity. This is basically the logarithm of power. You see lower left, power and frequency, power on the y-axis, frequency on the x-axis. And you can see clearly the slower frequencies on the left of the x-axis have much higher power than the other ones. So now the question is, so this provides you with one measure of temporal structure. We currently use, we go a lot into engineering and information theory to get different kinds of measure of spatial temporal structure. So I work a lot with engineers these days to get these different measures of temporal and also spatial structure. So the question is whether this power law now has something to do with your sense of self. And this is what we tested in this study. It's done by a postdoc of mine, Zirui Huang, originally from China. So he was very interested here, again, the temporal structure of the resting state and whether that is related to self-consciousness. So what he did here, he measured the resting state in fMRI, so in the very slow frequencies from 0.01 to 0.1 hertz. And for the experts among you, these infra-slow frequencies have very long cycle durations. So long cycle durations, which are ideal for integrating different stimuli, providing temporal continuity. So, and on the psychological side, he used a particular instrument which is called the self-consciousness scale, which includes 3 different dimensions: private, public, and social. So, the first thing, he characterized the resting state itself with what is called the power law exponent or scale-free activity. You can see here the 2 main regions. You had them before, the medial prefrontal cortex and the posterior cingulate cortex, where we observed the strong overlap between resting state and self-related activity. And you can see on the y-axis the power, and on the x-axis the frequency, and you can see the slower the frequency on the left of the x-axis, the higher the power. And each line is one subject, and you see there's a huge inter-individual difference. This is not noise, this is an intrinsic feature. I know that the statisticians tell you inter-individual differences are bad, they are noise, you want to cancel them. For me, they are the target variable, because if your resting state encodes information about yourself, all our selves are different, you should have inter-individual variation in your spatial temporal structure. And that's exactly what you can see. We have the same findings currently replicated in preparation. So then we looked whether these curves, this temporal structure, in the spontaneous activity was related to self-consciousness, and that's exactly what we found here. You see here, particularly the left graph, you find in the private self-consciousness, you see the more private self-consciousness you have, the higher your power law exponent, and that means the higher the power of your particular very slow frequencies. The slow frequency, remember, they have the long cycle durations and they provide temporal continuity. So that makes perfect sense. So private self-consciousness has something to do with the temporal continuity of your spontaneous activity. And that's exactly what your sense of self is about. It's a temporal continuity. It goes on and on and on throughout your whole life. It's quite an amazing thing what your brain does. Yeah. So that, and we have currently other findings. We have the same finding now in EEG in the faster frequencies. We're just about to submit this, and also with other measures of the spatial temporal structure. So, why is that important? So now you might say, maybe my self is just locked in here and the spontaneous activity spatial temporal structure. So then why is it possible that myself is also sensitive to the environmental demands, the context? So I get changed by certain environmental events, particular major events, which might even induce a post-traumatic stress disorder. And there are a lot of cultural impacts. Andrew knows that very well, that my sense of self is also changed by the cultural context. So here I present you one study where we did again spontaneous activity, and we investigated the brain spontaneous activity in the while they were adult, and we applied a questionnaire, childhood traumatic questionnaire, CTQ, to measure the early traumatic life events in childhood. So in the hypothesis, maybe the spatial temporal structure is somewhat sensitive to early traumatic life events. And that's exactly what we found. I go to this slide. Look on the right lower graph, again here on our preferred region, medial prefrontal cortex. And we measured the degree of entropy. It's basically predicting one time point to another, the pattern, and in a more common sense way, entropy is about disorder. If you have high entropy, you have a lot of disorder, and the way you sit here, that looks like there's not much entropy because you seem to sit very orderly. But however, if you were sitting all over here, the whole room, then there would be a high degree of disorder because I could not predict from what I see the next row. Yeah? I know it's a bad example. Yeah. So anyway, so same in the brain. The higher, and this is interesting here, lower right, the higher your degree of entropy / disorder in your spontaneous activity during adult, the higher your degree of early traumatic life events. So meaning early traumatic life events disrupt the development of a coherent spatial temporal structure. And again, if you do psychotherapy, you know this very well. Yeah? Many psychological problems, many psychiatric disorders have early developmental changes. Freud was right in that sense. Yeah? There's absolutely no doubt. Yeah? So meaning that your spontaneous activity is not just locked in the brain. It's highly sensitive to its respective environmental context over time. Yeah? And that's what you then see, for instance, in cultural neuroscience or also in psychotherapy. So, I want to show you now, I make the smooth transition to somewhat psychology and then psychiatry. Here's a paper which I do is Andrea Scalabrini did this as a postdoc of mine in Italy. He's very interested in personality disorders, and he's also a psychoanalyst, psychotherapist. So it's very interesting. He really does both. So the idea is here that is a pool of healthy subjects, Italian healthy subjects, and he measured the narcissistic features in them. Because I'm explicitly saying here it's Italian sample because there might be cultural variation in the degree of narcissism between different cultures and samples. Yeah, and here we said, or maybe the spontaneous activity is somewhat related to narcissistic features. And here we showed, we presented a task where they had to touch an animated, real person target or a non-animated, an artificial hand. So first we wanted to see how much neuronal activity is elicited when they have contact with the real world / animate target or the artificial world / artificial hand. And interestingly, for insiders who know this, one of the main regions which came out here's the insula, closely connected to these cortical midline structures, and even more interesting is the right insula. It was highly correlated with narcissistic grandiosity, meaning the more activity, I put it the other way around, the less activity the anticipation of the animate target elicited, the higher your narcissistic grandiosity. What does this mean? It means, and that's very typical, when you have the contact with narcissists, they have real problems of intersubjective relation on the same level because they're so much into their self, they cannot relate to the other self. So there, the balance between the self and the other is completely tilted towards the self. And that means sense that they cannot elicit proper activity in response to external or non-self stimuli. Yeah? So then we looked into the spontaneous activity. So if the hypothesis is right, that the spontaneous activity and its scale-free activity, what I showed you before, the power law, these frequencies, contain information about the self, then you would expect that this is predicted by the frequencies of the resting state in these patients. And that's exactly, interestingly, is a completely different study sample. That's exactly what he found here. You can see here, lower left, the more scale-free, the more slower frequencies he had, the less activity they could respond to the external stimulus. Meaning, the more internally focused and the more slower your frequency are internally, the less you respond to the external world. And that means the more you are focused on your own self. Yeah? So basically, in a way, if you want to say so, because your intrinsic, your spontaneous activity is relatively slow in this, you focus more on your own self, and you're too slow to respond to the faster environment. Because everything which comes from the outside world is usually faster. So you need fast frequencies in your brain to respond, for instance, to the stimulus. If you don't have these frequencies in your brain, in your visual cortex, or that they are very low, you will not perceive this consciously. Yeah? If your slow frequencies dominate, then you probably don't even perceive this. You're just in your own thoughts, and you say, what strange things this guy does. Yeah? That's probably true anyway, but yeah. So that's so basically, you might have here, and I think I show it in the next slide too, it's more or less the same thing. When you start in the bottom, your spontaneous brain activity seems to be very slow. And it's too slow to respond to the external stimuli. So you have a disbalance, read on the left here, between the internal mental world / the internal, the speed of your internal mental world / your neuronal activity / your spontaneous activity, and that you cannot properly respond to the faster stimuli. So, and that's something now we are currently testing, that we look, really we present stimuli in different frequencies and see that the response is dependent upon your internal mental / neuronal speed. And if that holds, that might also open up new lines for therapy, psychotherapy, that you present stimuli and certain frequencies tailored individually and try to strengthen or weaken certain frequencies. For instance, with brain-based individually tailored music therapy or physical therapy, dance therapy. So that's my hope. So now I show you another example how this approach works, mainly from psychiatry. And it's the last part of my talk. So I will focus mainly on bipolar disorder. Bipolar disorder is a strange thing because patients can be either depressed or manic. And the same patient can be depressed and at some other point manic. Manic means when they're extremely happy, they run around like crazy, they do all kinds of sometimes crazy stuff, and the happiness is usually contagious. Yeah? So if I were manic, I would run around like crazy here, and you would basically say, what is this guy doing? Yeah? And depressed, obviously, is the opposite. You sit still in the corner and don't move, and you're completely sad, and you have your own internal ruminations. And you can see already while I'm talking about it, I adapt to that mode. So the question is, where does this come from? And so here we investigated the spontaneous activity of these patients, and we focused on two particular networks in the brain, the sensory-motor network and the default mode network. The sensory-motor network, as in its name, is closely related to processing sensory stimuli and also motor activity. Why is that network relevant? Because in depression, the people sit in the corner and don't move. And the manic patients, I showed you, run around like crazy. You have also an intermediate case, depression agitated, where they are very anxious and move around a lot. We have data on that. I will consider that later. The default mode network is mainly the network here in the middle of the brain, shows a strong, includes the cortical midline structures, and has a high level of spontaneous activity. So, and now we looked, and the default mode network, as I already said, has something to do with your sense of self, your ruminations, mind wandering. So it's all a lot of internal mental activity. And in depression, you know that this internal mental activity is too strong because they have all these kind of thoughts going on and thoughts of guilt, and I'm not worth it, and my hospital stay cannot be paid for, I'm too poor, and so on and so on. But it's all focusing around the own self. So we described it as an increased self-focus. So now we looked for these networks, and the first thing what we observed, and we looked particular for much is done for functional connectivity, the highways between the different regions. What we looked, hoopla, this sounds different here. We looked particular for how much the activity changes. So we basically for neuronal variability. So how much the activity in these networks changes across time. So basically we looked for a neuronal measure that corresponds to the speed of activity, because the change describes your speed. Yeah, if I do a lot, you say I'm high speed, I do a lot of change. If I don't do anything like this, and speak always like this, you find it completely boring and there is absolutely no change. Yeah, and this is what we observed here in the depressed patients. You see the upper line, the purple. You look in the middle, the default mode region. You see a lot of change. Yeah, so here when you look the very upper, the brains, the red dots are the default mode regions. You see the regions you already know. And the blue lines, the blue dots are the sensory-motor regions. And you can see that in the depressed is the purple bars. You can see that the default mode regions show a lot of variability. That makes perfect sense, because they have these continuously ongoing changing thoughts and all ruminating about their own self and their bad negative emotions. Whereas in sensory-motor region, the purple, you don't see much variability. Meaning, if you don't have much change in your neuronal activity, you have a higher likelihood that movements are initiated. Meaning, the patients sit still in the corner and don't move and don't walk. And then you see the balance on the very left is strongly tilted towards the default mode network. Compare that with the balance in the lower row, the gray bars, which are the healthy subjects, and the euthymic subjects. So you see it's abnormally tilted towards the default mode network in depression. Whereas in mania, you see the opposite. You see in the middle, the yellow, you see a decrease in neuronal variability in the default mode network and relative increase in the sensory-motor network. So and that means they move a lot. And after this finding, I asked them, what do you think while you're in mania? Because from these findings, I would expect that they don't have many thoughts. And that's exactly what the patients told me. So when you calculate the ratio, upper left, you see tilted towards the DMN. You see that DMN is the depression is the purple bar, upper left, and the manic are the yellow. And you see that the euthymic, the bipolar patients who are not in depression or mania, and the healthy are somewhat in between. So and then that also interestingly correlated with the depressive and the manic symptoms. This is what you can see here. Upper is the correlation with the symptoms. You see we correlated the balance between the thoughts and the movements between the DMN and the sensory-motor network with the depression score, and you see the more that balance tilted towards the internal state, the default mode network, the higher your depression, whereas in mania it was exactly the opposite. So if you want to summarize this, this amounts to this. So here, the upper basically reflects that your disbalance between the sensory-motor network and the default mode network. You see, usually the balance is sort of even, but here in depression it is tilted abnormally towards the default mode network because they have increased variability, and that leads to increased internal thought, self-focusing, rumination. And also ultimately, we also observed increased variability in the insula, increased focus on the own body, somatization. Whereas, but nothing is for free, as we all know, no free lunch, that in the sensory-motor network you have decreased variability, meaning they don't move, psychomotor inhibition, retardation. And in mania, you see exactly the opposite. You have psychomotor excitation, here lower left, and this leads to hyperactivity, and they continuously talk, much more than I do now. Yeah? And on the other hand, probably their variability in the DMN is decreased, so they have less internal thoughts. Their thought contents are completely determined by the external world, and that's really true. Yeah? So they're easily distracted. Yeah? And they immediately pick that up because to fill their sort of inner emptiness. So I'm present a couple of more slides, one more study on these bipolar. And one central component is your time consciousness. And the idea is, and you probably got that many of these mental features, like sense of self, consciousness, psychiatric symptoms, are, in my view, temporal or spatial temporal abnormalities. They are organized in an abnormal spatial and temporal way. The function itself, the cognitive function itself, might still be okay. The pure processing of contents is normal. However, the contents are processed in an abnormal temporal context. So imagine short-term memory, working memory. You have to memorize now what I'm saying from moment to moment. So this requires a certain faster frequencies, because maybe I can talk a little slower to adapt to your slower frequencies. Yeah? However, now imagine that you are very slow in your brain. You will not be able to follow me. You will have a lot of problems, and in your working memory, you might not remember because the item comes too fast for your frequency profile of your brain. So, and that's ultimately an important point then also for therapy. You want to adjust, normalize the frequency pattern. So here, I show you one last study on this. When you ask these patients, there has been a very rich literature in what is called phenomenological psychiatry, which basically focus on the subjective experience of these psychiatric patients. And what you typically have in depression, the speed of inner time is too slow. When you ask the depressed patients, nothing changes, nothing moves, and it drives them crazy. And of course, it's completely normal. For you, it would be the same way. If you have the feeling that nothing changes, everything is the same, because you become sad and depressed. Yeah. So for them, the inner time speed here on the x-axis indicated is extremely slow, and that means they are too slow for the outside world, the outer time. In mania, it's exactly the opposite. They're extremely fast. That's why they walk so fast, speak so fast and everything, because it's their inner time. They just follow their inner time. Yeah, meaning you or we are too slow for the manic patients. He's desynchronized. So this is what I show you here, because the way we perceive the external world, the time speed in the external world, strongly depends about our inner time. Yeah? So basically we compare the outer time with the inner time speed. Neuronally, it means the speed of the external stimuli depends on how they are processed by the speed of the spontaneous activity. So basically your spontaneous activity provides a baseline. Now, if your spontaneous activity and its time speed here on the left are too slow or too fast, you will perceive one and the same stimuli, external stimuli, in different ways. I give you a clinical example. I was talking to a patient in China, a young girl, and she very depressed, and she told me that I know that my mother speaks in normal pace, in normal speed. But for me, I cannot follow her. She is simply too fast, and that's why I don't speak. She was completely mutised, and she told me that afterwards. So her inner time speed, and also she didn't move, and then she also told me, everything is too slow for me. So she didn't speak because she perceived her mother speaking as too fast. Why? Because her inner speed was too slow. Yeah? So everything is relative. Yeah? And that's the problem. So now the question, how does that is manifest in your spontaneous activity? So what we measured in these patients then again is the degree of change of neuronal activity, meaning neuronal variability. And we looked in two different networks. We looked in the network, the neuronal speed in the network that mediates inner time speed, and that is well known as the sensimotor network. And we looked in another network, which is also well known. We looked in the visual network, because we said in the sensory network, because that is where the external stimulus is processed. So if you perceive the external stimulus as too fast, you would expect that you have too much neuronal speed, a lot of neuronal variability changes in your visual cortex, because that's the first point where your external stimulus comes in, and then if that is too fast in the brain, spontaneous activity in sensory cortex, your stimulus is perceived too fast, or the opposite as too slow. Clear hypothesis. So we expected in mania, that they have lower variability in the external time speed / in sensory cortex, because for the manic patients, we are simply too slow. They perceive us as slow. External time is too slow, and of course, when things are too slow, of course, what happens? You become impatient and get angry. Why? A little bit faster. You can't follow me. What is this? Yeah, very normal reaction, and that's exactly what we saw. That's the variability in the sensory-motor cortex upper left was higher. The inner time speed on the neuronal level in maniac patients in the sensory-motor network and in the visual network the other way. Look at the depressed, the blue bars, upper left, it was exactly the other way around. Neuronal time speed / neuronal variability was too fast in visual cortex. You see the high bar, whereas it was very slow in the inner time speed, the sensory-motor network. So exactly what you see phenomenologically, and you see then the healthy subject is, you see they're plus minus balanced. And they're balanced, why? Because you're somewhat synchronized. You somewhat are in tune with me. It's in the same way when you dance to a certain music, you dance the tango, and you align yourself with the rhythm of the music. However, if your internal time speed is too slow, you will always miss the right rhythm. Or the opposite, you're too fast. And that could be a wonderful example for really brain-based dance or music therapy. That you try to change this frequency, that you normalize their speed, and by that you hope, at least I hope, that you improve their psychomotor behavior and their cognition and their time speed. Yeah? So when you calculate the ratios between inner outer time, sensory-motor, visual cortex, that's what you get here in the lower left. Let me summarize this. I skipped that one. So here, this is what we usually have, and this is what really the findings show. So we have the inner time, it's a sensory-motor network, and it's somewhat in tune, balanced, more or less. There's very dynamic, of course. Sometimes the inner is a little slower, sometimes the outer is a little faster, and it always attunes to each other. Yeah? And you see somewhat a balance. So this balance corresponds to this finding upper right, the healthy subject, where you see the two networks, sensory-motor, visual, somewhat balanced. Now, in depressed patients, you have this. Your inner time speed is too slow, left, meaning you have not enough neuronal time speed in the sensory-motor network, decreased neuronal variability, and that means you experience your inner time speed as too slow. Nothing happens. Nothing changes. Monotony is the same, and nothing changes. That's exactly like depressed patients speak, because there's no change in their neuronal activity. It's always the same. And they're very aware of that, and that drives you nuts. However, and at the same time, they experience the outer time, what happens in the outer world, as way too fast. Remember the high bar, here I show you this one, and this one. Middle blue bar, high bar. Extreme strong variability in the visual cortex. That means they perceive visual stimuli is way too fast. And that's exactly what people report. So we're currently doing the same experiment now with time perception measures, combine that, and visual analog scales for subjective experience. So here, in mania is the opposite. Your inner time is too fast, so you have high neuronal variability in the sensory-motor cortex, whereas your neuronal variability in sensory cortex is too low, meaning you perceive the external world as too slow. And as I said before, of course, when you're too slow, then of course I get impatient. I said, faster, faster, why can't you follow me? And then you get angry and aggressive, ultimately. And that's what you see in these patients' behavior. So, come to the end. I hope I made at least a little impression, if not a case, for that maybe this spatial and temporal features of our spontaneous activity are relevant for mental features. That psychiatric symptoms, I showed you for the bipolar, the sense of self may have a spatial-temporal basis. It's the spatial-temporal framing. The context, the spatial-temporal context within which specific sensory or cognitive contents are processed. And that yields that spatial-temporal, the integration of these cognitive or sensory content within this spatial-temporal structure, that what decides upon your mental features. Whether you have a sense of self, whether you're conscious, or whether you have abnormal psychiatric symptoms. And that ultimately what I would like to see from you as psychologists and psychotherapists, that we specifically target these spatial-temporal features. Remember the sense of self with the power laws, the scale-free activities, these different frequencies, these curves which I showed. If you can manipulate that, and if you change your sense of self, you perceive the world in a different way. Yeah, you have different cognitions, because it's really the self is, of course, underlying all your perception cognition. Very important. So I consider the self not as a higher order cognitive function, like a meta-memory, like Hakam Lau. I don't, because that's a very Cartesian model which goes back to Descartes, or Kant, yeah? As much as I love Kant, in this case, I say no. That's central, yeah? So I consider the self as a very basic, the most basic spatial-temporal organization mode, and if that is changed, your consciousness, your relation to the world, and your behavior, your cognition, your emotion, your working memory, your attention will be changed. And there's more and more data supporting such a view. So it really, as you see, it turns it around. Remember the initial 2 slides about the model of brain which I had? Yes, ultimately leads to this. That you construct the time and space in your brain, I'm speaking here of construction of time and space, in a very individual or self-related way. And that ultimately leads to what I like to speak of spatial-temporal psychopathology, and you can see, I hope, that provides you some idea about the second model of brain, which I said, where the brain is not like a car. Remember this car within the spatial temporal trajectory, or my example of the tennis player. And that's exactly what your continuously your brain does, and that these spatial temporal patterns contain a lot of information, and we're currently just scratching the surface of that. And I think that's why I wrote Unlocking the Brain, and that title was exactly that. My hope is that the spontaneous activity and its spatial temporal structure really can provide us a key to the brain. In the same way, once we knew that the heart is a pumping organ, it pumps blood throughout the body, probably suddenly it made perfect sense that the heart is a muscle, it has electrical activity, and so on and on. Same with the brain. Thank you very much. Yeah, good question. I think what we first distinguish in psychiatry is between state and trait markers. So state markers are those markers which are related to the actual symptoms. And I think that the data I showed you, they're really about state markers, because you did not really show abnormalities, particularly in the SMN-DMN balance in the euthymic patients. However, we are just about to submit papers about findings. That's very interesting. In the euthymic state, that they have decreased activity in perigenial anterior cingulate cortex, a region which is closely involved in self and emotions. And that makes sense, because even in the euthymic state, these bipolar patients, they all report a certain self-instability, because they're always fluctuating in their mood. They never really know who they are. Many patients tell you that once you ask for them. The traditional DSM-oriented psychiatrists never ask for these questions, because the self doesn't exist in DSM. Yeah? But the self exists a lot in European psychopathology, where I'm coming from, particularly in Germany. So, and I think that is very relevant for the brain. So, and there also this mood instability. So it's a very interesting finding. So that would be, for instance, a trait marker. Yeah. Yeah. Mm-hmm. Okay. Yeah. Okay, good questions. So first question, anatomical specificity. I know that a lot of, particularly the Human Brain Project in US, it's basically all about this, trying to make more specific anatomical mapping with more and more refined technique and subregions here and there, and which on a functional level is supposed to correspond to the representation of specific contents. That's the first model of the brain. And I tell you, I would argue it is not a cognitive specificity, it's a spatial temporal specificity. So what do you mean? You mean the EEG mapping upon the anatomical structures of the brain? Yeah. So usual measure, one new method you can use Loretta, obviously, which EEG localization. So I'm not a big, so it's always problematic. So if you want to have localization of these faster frequencies, you probably need to go into MEG, or we are also doing ECOG and SEEG intracranial. Yeah. But for me, the localization is not that important because I consider not the localization, but I consider the region in terms of temporal features. So what does this region contribute in temporal respect? And I give you an example. I was always asking, why are these cortical midline structures so much involved in this? And one answer I can currently give, that they show a very strong power in the infraslow frequencies when compared to sensory regions. And that makes sense. Your sensory regions show a lot of relatively more faster frequency. Why? Because they continuously have to respond to the fast frequency input. Whereas your DMN is left relatively in peace by the direct sensory input. It sort of operates more in the background, so it can do whatever it wants, so it can focus more on the slow frequency stuff. That's an explanation, yeah, which is not, but that finding is clear. So what we're currently doing, we're trying to do the map. We do an anatomical map of the brain, and we try to look each region, give a temporal profile with different kinds of measures. And from that temporal or temporal spatial readout of the resting state, I hope that I can predict behavior and task-evoked activity.
All right, so that's it. Really appreciate you coming and sharing your latest ideas with us. And I want to thank you for coming, and that is it. So please join me once more in thanking Dr. Northup. Thank you.
Thank you. Welcome.
Okay. Your computer survived?